Hello. I'm supposed to have my slides up. I'm Daniel, and I will be talking to you about bringing your own data and building better AI applications. Just need to get those up on the screen. Give me a minute. Okay, I have informed someone and they'll help me out with that. In the meantime, if you have any sort of prior questions, happy to tackle those. I'd love to know if anyone has experience building with vector databases or implementing any sort of RAG workflows. Okay, my slides are up. We're great. Okay, so like I mentioned, I'll be talking about building better AI applications. With the context of bringing your own data, I'm Daniel Phiri. I do developer experience at a company called Weaviate. You could see the logo at the top of the slides there. And you can find me anywhere online as Malgamviz. Right, so getting into it. Again, I think I did ask, have you ever used a vector database? Definitely drop something in the comments if you haven't. I definitely use them quite a bit. And have you used ChatGPT or any chat application? I think there's a really interesting one from Mistral called La Chat. At this point, you probably have. I wouldn't be surprised. And last question, have you possibly heard of RAG? If these are new concepts to you or have no idea what I'm even asking, hopefully at the end of this talk, you have a better understanding of vector databases, tools like ChatGPT, and RAG, which stands for Retrieval Augmented Generation, by the way. Right. So, like I mentioned, I'll be talking about how you can bring your own data and build better AI applications. And to sort of drive this point, I want to go back to where we started with artificial intelligence, what we've been doing, and where we're possibly going. Right. And so in the beginning, we had Neolithic man, right? They would do cave paintings. And this is how they communicated. This is how they would show and document. And this is where people went and saw how people lived in that specific time period, right? This is how we know how Neolithic man lived. We look at these cave paintings. If we think back to the Middle Ages, this was the paintings that people put, the paintings artists wrote or created, described that time really, really well. And if we go back to today, it's mostly Twitter. Modern society is like we could sort of gauge the temperature of modern society based off what people share on that specific social media platform. And if you explore this and use Twitter to explore how LLMs have come up and where we've gone and where we're going to, we start with the rise of large language models, right? Transformers 4 years ago, a couple years ago, more than 4 years ago, were invented, and about 4 years ago, ChatGPT, the first version, or at least the first version that reached the mainstream, came out, and then GPT-3 really sort of came to the mainstream, and this changed a lot of the way we used applications and interacted with software. ChatGPT was one of the fastest growing software products, if not the fastest. And then you saw people starting to build on ChatGPT. It was outside of this chat that we had. OpenAI opened up this API for developers to build from it. And at the bottom of this slide, you can start to see companies doing interesting things like Ask Viable using GPT-3's API to build insight from customer feedback, right? Algolia started to use GPT for customer interactions also. And it was mostly very conversational. And then we started to see this age of hallucinations. We were really excited about this piece of software. We're excited about where we could take it. We were excited about what we could do. But then we were met with the concept of this experience of hallucinations. And so, if you know anything about these large language models, they're trained on a specific data set. And so, all of their output is at least supposed to match the data set that they were trained on. But these models predict the most likely uh, next token per se. And so a lot of the times those predictions come from outside of the data set. And that's a huge problem because they end up saying things that aren't true or things that do not even exist. And these hallucinations can be quite funny, as you see here in this screenshot. And at best, they're something to laugh about. And at worst, it's a really big problem for your company because you start to you have less of a sense of control over what your users get as they interact with your company and the experience you build around your company, particularly for people building them around these customer interactions, right? It could be a huge public relations problem. And this really funny example that you see in the screenshot is one LLM basically said you can melt eggs because of an article that it found. Someone joked about the fact that you can melt eggs. And so when everyone started to build these products around LLMs, when people asked, can you melt eggs, which by the way you cannot, these LLMs just sort of kept giving this response that yes, you can. And then this hallucination from ChatGPT, as you can see highlighted in the screenshot, became an actual answer that we have on Google. And this is just to drive the point that hallucinations, although funny, can be a huge problem, specifically for use cases that are extremely, extremely important for our applications and our users. And this interaction and what I just explained highlights a couple problems that we see or we have or we've started to notice in using large language models. One, you have out of date data. A lot of these models work with data that had a stop period, right? It was a specific period of time that you trained this data, this LLM with data from, and then you release this model. So we keep having these updates coming with these models. Another issue is we can't really refer or reference these sources or reference um, the origin of these predictions from LLMs, right? It's somewhat of a black box when we think about it. We have really no idea of knowing this prediction came from this specific place because this is just what the LLM outputs. And then of course it goes without saying that there's a huge security and privacy issue that comes with having specifically customer data um, interact with a tool that is behind another company's data, for example. We have a lot of these model providers that we shouldn't really just trust blindly. And security wise, a lot of companies, a lot of industries have laws and compliance regulations around what you can do with your customer data, with your user data. And so these are a couple problems. Fourth problem, because I can't count clearly, is the spelling there. But let's go for it. And just to highlight this interaction with LLMs, I'd like to think about them as exams, right? So I think we've probably been in this situation. If you've been in sort of like a schooling or school environment where you have an examination and you do not know the answers, right? And so you start to make things up because you know vaguely around the topic, right? And you have to write an answer because this is an exam that you have to write and you probably want to pass. And this is the same thing LLMs do. They do not know an answer, and so they make something up. And a solution to this giving a sort of going along this examination analogy, is to make this interaction with large language models an open book exam. What that does is it solves the three problems that I highlighted. It gives large language models the ability to source this data and reference where they got that information that they're giving us, right? So if you ask a large language model, can I melt eggs? Having this open book exam like interaction with that large language model makes it much easier for you to source the data that helped it give you that answer, right? And in this case, you'd probably get that article and then you'd know this is probably something someone was joking about. And the second thing is it helps LLM have context for the interaction that we're having, right? If you have an open book exam and you're asked a question about pre-flight, for example, or um, the physics of flight. If you have a physics book, you have context for that answer you're going to give in the examination, knowing that this is a physics exam and I should give a physics answer, rather than opening a 18th century book about mysticism that talks about flights in humans, right? That's not the type of answer that you want to give in an exam where you're asked to explain flight, right? It gives you context. And then the last thing is you have way more control over the data that you can give it. Like I mentioned, a lot of organizations have compliance regulations around the type of um, interactions that their user or customer data can have with external systems. And so ideally, you do not want to be handing over this data um, that is supposed to be secure and abstracted away from third parties to third party applications. And so having this open book exam, and you'll see later, helps you have this sort of interaction. And this is where I introduce something called RAG. RAG is an abbreviation that stands for Retrieval Augmented Generation. And as it sounds, you retrieve information, you augment it, and then you generate. And so this is a concept that a lot of people are using to sort of combat these bad actions or these hallucinations from large language models. And so in a lot of our interactions, we start with this query response type of interaction where on the left here you have the sort of interface that the user is interacting with. And on the right here, you sort of have this large language model. And ideally, what we do is we put in a query, the large language model would service that query, and then we get a response. Now, what RAG does is it sort of builds this workflow in between us getting that query and getting that response to sort of combat these hallucinations. And so we'd start with a query. Of course, we always embed these queries because large language models, especially if you will do the retrieval, do not understand text. And so we create vector embeddings for these queries. We then retrieve everything relevant to this query. And then whatever we get back from this retrieval, we add this as context to then augment our prompt. So our original prompt was the query that we put in, and then we fetch information relevant to this query, we get context, and then we pass this context as well as the query to the large language model. So in this case, back to the um, if you want to give a more contextual answer, for example, I work at Weaviate, and if I want to know what the latest way to initialize a client is with uh, with Weaviate in TypeScript, instead of passing this question to my large language model, knowing that we have a new version of this client, it will definitely not know that answer. I store all my information, all my documentation on the new Weaviate client in my database. And so when I say and make this query, what is the latest way to initialize the Weaviate TypeScript client? I then fetch all the information relevant to this new Weaviate TypeScript client and then pass whatever results I get back and be like, from this information, what is the way to connect to a Weaviate client? And then that augmented query that is the query plus the context we get from our retrieval, is then passed to the LLM, and then the LLM creates a more contextual answer and a more accurate answer, ideally. A big analogy people give is retrieval augmented generation is like giving a large language model blinders, right? And so just to go through these steps, as I mentioned, the retrieval stage is where you have this user query fetch relevant information from a vector database. Ideally, you have all this information stored in a vector database. And if privacy, for example, is an issue that you have to take care of, you could use an open source vector database. So you have this on your own servers. You don't have to have this deployed on someone else's cloud. And so you retrieve this information that is relevant to your query. And post retrieval, you augment this original query that would ideally before be passed to the LLM directly. But now we get the original query and the context that we retrieved from our vector database, and we pass this to our LLM to actually generate data based on all of this. And the idea here is we get a more accurate generation or a more contextual generation, having that augmented query with relevant information. And that's just sort of to remedy this. I will demo something called Verba, which is an application built by the very talented team at Weaviate, and it's an example of a RAG application. And so I will open this up. Excuse me, and I'll just zoom in a bit. And so the idea here is you have this chat that you can interact with, and we have indexed all the Weaviate resources and documentation, and so I could type things here. So what is a planet? That's also a good question to ask. Oh, lovely. Right. So also I have a document uploaded here. And so this document is a PDF of a camera that I bought. And we'll just get rid of this actually before this says offline for some reason. Yeah, we'll just reset. Okay, I'll just check my terminal really quickly and make sure that I have everything running. Okay. So I have that running, and I can actually go and search. Status, just reset. Okay, so we have everything reset. Now we can do a search. We'll say hello. Your Verba has no data yet. And so what we could do now is add some documents. We could chunk a bunch of different things. And so I will grab a PDF. And so let's import a PDF file. I'm sure I have a couple PDFs here. Looking for one with text. And so let's get a receipt that I might have. Okay. We have a French exercise here. And this is supposed to have said oh, I clearly did not appease the demo gods today because this is not working as it should, but we'll figure it out as we go. Okay, there we go. So we have that imported, and it actually chunks it now. So imported one document and one chunk. And let's go to our search. Hi, what is this document? And so the document I uploaded was the PDF. And weirdly enough, it is getting the wrong chunk. So I'll just reset this again, and let's try this one more time. Sorry for the issue here. And so I'll go back down and grab that PDF. So this is something that I have running locally, and if this doesn't work, I will use the bizarre. I will use the deployed version, which I know will work. Okay. Interesting. Okay. So back to search. And if we go and look at our documents, we have this document, right? That's perfect. Hello. Very weird. Right, let's just go to verba.weaviate.io. And we'll refresh this. And so the idea is you pass context into this application, and then based off that context, you have a response. And so, like I mentioned, we have the context here being a blog and all the information that is available on weaviate.io. And so I'll ask, what can you tell me about TypeScript in Weaviate? Right? And so because we do have a blog post that came out and we released on our blog about the new beta of the TypeScript client, this is the information that we get. And so this is the answer that we have, and we get this very concise, curated information on how we can actually do things. And I could ask, what changed in this client? And so then based off that information, and here you can see the context it actually used to give us this answer. And so we can trace that information. And so I'll ask a specific question. Does the client work on that's the TypeScript client. Does the TypeScript client work on client-side JavaScript apps? So this is something very specific, but also honestly only mentioned once in this blog post, and we get the answer. The client only supports Node.js server-based development, and this is incredible. And here we have the context that we got, and in this case, the context is the client library on the Weaviate page. Do you have demo apps? And is the documentation updated for the new client? I'll leave these typos in just so you can see that this is a very human-like experience as we interact. And so this is the idea of getting that context, and very importantly, having every single element that the LLM used to generate this answer, and then populating this field. And so if the demo that I wanted to show worked, we would be able to upload, and you can do this when you have your own version of Verba running. And here you could see all the documents that we were using to power this. And so this is the idea of retrieval augmented generation and how it works. And let's move on a little, right? So we've seen what retrieval augmented generation is and the value that it can have for organizations in giving organizations more security, more context, and more control over the data that their LLMs access, or the responses that the LLM gives by controlling the data that your LLMs have access to. And then this also solves the problem of hallucinations, and it just makes you way more secure in shipping these AI native applications. And a big part of this demo, like I mentioned, was Weaviate. Weaviate is an open source vector database that you could deploy to your cloud or use the cloud offering that we have available. And you might be asking, right, what is the relevance here of a vector database in this RAG implementation in sort of combating this idea of hallucinations in large language models? The idea here is the most, or not the most rather, I don't think it's the most important, but a really important part of RAG is the retrieval portion. Because based off what you retrieve, your LLM then generates responses for. And so you want to sort of streamline and make your retrieval as efficient or as effective as possible, because the better your retrieval, the better your results. And from building these AI native applications and supporting AI native developers, we found that similarity search, semantic search, is really best suited for this retrieval experience. And what is that? Sort of just contrast what it is. I'll introduce the idea of traditional search, which was mostly a keyword match. And so in this example, I ask, why do airplanes fly? My response would be, you should fly with a expensive airlines, which has no relevance to the question that I actually asked. But you could see that we have a keyword match in this. And so to sort of flip the coin here, similarity search grabs the context of your search terms and your queries and gives you answers relevant to the answer to the search term. And so it has this context, this understanding of that query, and then gives you the most relevant responses. And this works with large language embedding or machine learning models. And so the idea here is you have a machine learning model that is built to understand data in a very specific way. And you have this subset of machine learning models that people use to create abstractions of data called embedding models. And so you have your information on the right here, and you pass that information, your data, your objects, your blog posts, your images, you put those into a machine learning model, and you create vector embeddings. And these vector embeddings are an abstraction of your data in a format that the machine learning models and other machine learning models can understand. And so this array of numbers that you see are called vector embeddings. And so to sort of connect this to what I talked about before, similarity search, we grab all our data, be it this blog post or this result on flying with expensive airlines. We pass that into our machine learning model. We get our vector embeddings. We do the same thing with our actual answer and all of our other data, um, actually, and pass that through our machine learning model and get our vector embeddings. And then what we do next is plot this or put this data in a vector space. And this vector space is this collection of all these vector embeddings. And because of the characteristics of vector embeddings being an array of numbers, we can have this multi-dimensional space that stores these items. And based off the dimensions in these vectors, they tend to appear in different parts of this multi-dimensional space. Here we have a three-dimensional space. just to sort of illustrate the idea of the placement of these objects in this vector space, where we can see similar items are grouped or tend to be closer to each other in this multidimensional space. We have an apple and we have a banana close to each other. We have these tech companies, Google and Apple, close to each other, and animals here close to each other, sort of bunched up, having similar vector embeddings, which means their abstractions or meaning or the way the LLM understands them is sort of related. And that's the way you would see this. And so we have our data, we create the vector embeddings, we pass these embeddings into our, or we have these embeddings in our vector space, and then we can actually make queries. And so, for example, behind the scenes of a similarity search, when we say, why do airplanes fly? That query, that text query that we have, gets passed into our machine learning model, and then we create vector embeddings for that search term. We then get these vector embeddings that represent the search term that we created, why do airplanes fly, and have that in our vector space. And then, as I mentioned, once you plot these vector embeddings into this multidimensional space, related items tend to be close to each other because their abstraction by the model is very similar. And so we use this to our advantage and look around where we have our search term placed in our vector space and then return the most relevant items. And so we calculate the distance to the next objects uh, around our query in this vector space and then return those. In our case, the most relevant happens to be this NASA article because based off machine learning algorithms and different algorithms, particularly um, approximate nearest neighbor search, which is what we use to look around this item and then send back the most relevant. In our case, the NASA article was the most relevant after we ran that search, and that's what's returned. And so, in a nutshell, this is how similarity search works. And I think I alluded to it at the beginning. This is something that is built from the ground up in Weaviate to run and work like this. Weaviate was built specifically to handle and store vector embeddings of multiple hundreds to even thousands of dimensions in an effective way to sort of power this retrieval. And this retrieval happens to have a huge relevance in retrieval augmented generation. And so now you have an idea, where do vector databases actually fit? Like I mentioned, scale tends to be a big thing, particularly with storing vector embeddings. We abstract a lot of this information in documents or data, blog posts, articles, images. And once we have these vector embeddings with thousands of dimensions, it becomes really hard to retrieve these effectively in a lot of traditional data stores. It really creates a big challenge and makes computation very expensive. And so vector databases are built from the ground up to run specifically operations like these, from millions to even billions. And the idea of one creating these embeddings, running these searches, approximate nearest neighbor searches, looking for the relevant items around can be very computationally expensive. And so we want to be able to manage this and uh, at a very low level have efficiencies come in and things built to make this interaction and this search more efficient. And this is exactly why vector databases were built. And specifically with Weaviate, you can do all of these operations, run near vector searches, near text searches, where your inputs vary, and you still have these really quick interactions and responses, and tie that back to retrieval augmented generation. I'll show you a demo of a JavaScript application that sort of has this retrieval augmented generation capability in its what I like to think is in its most basic form, at least. And so we'll go into VS Code, but before we do that, we have this semantic search application. And so I currently have the top 500 songs of the century. And when I type, I could type anything. So songs about love. And so then I have this semantic search that's working and understanding the queries that I put in, and I'm getting songs about love. I could also say, please return songs about color. And I make that search. And so we don't explicitly mention the word color or any specific color. We don't say songs that have white in it. And so this is definitely not a keyword search, we can see. And so looking at the responses and the results that we get, we have all these items. So Pink Floyd, because we have band names being indexed. I'm Black and Proud by James Brown, The Whiter Shade, Homesick Blues. And so it really understands this concept. Or songs about North America. And when we make this, or let's try and even make this more abstract, and songs north of, songs about places north of the equator. Just sort of drive this idea that you get the most relevant objects. And so these are really interesting results. Let's see. Places north of the equator. And we get a lot of Earth vibes because there's an understanding that with the equator, we have the Earth. Okay, so this is the way our application works right now. And the idea now is to build this retrieval augmented application. And so here we have our, I'll just zoom in a bit. And so here we have our application. It's built in Nuxt.js. And so the front end of our application has a couple components that you run a search, you handle loading, and you display your results. And so in this results component, I want to add something extra. And before we do that, we actually have to communicate with Weaviate. And in my vector search, what I want to do is expand this search to a generative search. And this generative search is our idea of retrieval augmented generation. And because there's an element of prompting LLMs, what I'm doing here is I'm adding a grouped prompt, or a grouped task rather, and I'm saying based off these results. And I don't even have to mention that because that's there as the prompt is augmented. And so if I asked what is the best song, or rather ask something more contextual, if I make a search about songs about color, I could ask which of these songs is less about, is not relevant to this query. Let's do that. Which of these is not by a woman, for example. And then let's see what we get back. It's not performed by a woman. And so let's say songs about color. And and so we get this this answer. Say it loud, I'm Black and Proud by James Brown is not performed by a woman. And so you have that context of these results that we get. And then that's what we display. And we could change this prompt. And we could actually pass this to be more true to the idea. We can have the search term be the prompt. And so I will ask, what is a perfect song to listen to if I'm thinking about love, right? And so we want to sort of narrow the scope of the LLM in this case to the responses that we get. And so in the background, the search will run, will look for songs about love. And so instead of having the LLM look at all of the songs about love that are in its training data set, we'll only get responses based off the results that we get from our search. And so let's run this. So some perfect songs to listen to if you're thinking about love are: one, everybody needs somebody to love; two, when a man loves a woman; where did our love go? By the Supremes; four, love and happiness; four, your love is precious. And as you see here, we actually have references for the items that powered this response, right? And so I want to listen to songs about love based off the top 50 songs of the century from Rolling Stones and not from all the training data. And so this is the idea behind retrieval augmented generation. If I want to think, I could change this to what is the perfect song if what should I not listen to? So what one song should I not listen to if I'm going through a bad breakup, for example, since we're on the theme of love? So quick search. We Stopped Loving Her Today by George Jones. This song is known for its heartbreaking lyrics. And so this is the song that we get recommended. And all of this is very contextual information based off the response that we got back. And so this just drives the point that I was trying to communicate on how important retrieval is in having this type of interactions with large language models. And so just to sort of and go through what I mentioned. And so the idea behind what you saw me doing was an implementation or a JavaScript implementation of a RAG or retrieval augmented generation workflow where we have our query be augmented with a vector search that we have over our data to then apply context and then give this context and the query to our LLM and then generate more relevant information. And this helps us solve, one, the issue of the cut of training data in large language models. It helps us solve the issue of privacy and data ownership, where we can restrict the interactions that or the third interactions we have with third-party integrations. And of course, we have more contextual relevant results, more accurate results with this RAG-like workflow. And if you liked any of what I shared, here are the resources. I have a bunch of TypeScript resources on how to build applications like I just demoed. You could also check verba.weaviate.io out. And you could also check us out anywhere online. Thank you very much. This is all our handles, all the links, and my own personal handles. If you have any questions about building these sorts of applications, reach out. And thank you again. I hope you found something interesting from this session.